Okay, so last video we looked at some expressions to calculate magnetic fields from wires and stuff like that. So let's do some practice with that type of thing. So here we got a wire. I'm going to draw a magnetic field. So let's draw a magnetic field around it, something like this. And let's say the magnetic field here is 4.5 centimeters away from the wire, and let's say the field is 0.16 milliteslas. Okay, so let's see if we can find out what's the current in the wire. Okay, so first things first, I'm actually going to find out which way the current is going, and this where I can use my right-hand rule in order to figure it out. So my thumb is the current, my fingers are the magnetic field around the wire, and in order to do this properly, my thumb is actually going to be pointing down. So first of all, I know my current is going this way. So I can find out the magnitude of the current, and the expression we had last time was magnetic field from a wire. Let's use the shortcut version, 2 times 10 to the negative 7 I over R. Well, the only thing I don't have is the current, so I can solve for the current relatively easily. I've got the magnetic field, I got the 2 to the negative 7, I got the radius of 4.5 centimeters, and I can use all of them to then calculate the current going through the wire. And with that, I get 36 amps. So quite a bit of current actually, but that would be the current going through the wire in order to produce that magnetic field. Okay, all right, let's try a different scenario. Let's try something else here. So here, we'll bring these guys in. All right, so here we got 2 wires actually, and there we go, something like this, give them more room. All right, so we got 2 wires, something like this. Okay, now let's say this wire down here has got 1.8 amps running through it towards the right. And let's say right here at this location, let's go right there, and let's say this is 5 centimeters, and let's say this is 3 centimeters. And at this location right here, the magnetic field is equal to 0 teslas. So both wires are producing magnetic fields, and apparently they are canceling out at that location. So what I want to know is what is the second current in the other wire. Okay, well let's just start with the other wire first. Let's start with the bottom wire. I'm first going to draw my magnetic field for that wire, and if I do that, if I use my right hand rule, my thumb's pointing to the right, and I would have, these would be dots on this side for this wire, dots. And these would be where the X's would be. Okay, and I can calculate the magnetic field 5 centimeters away from that wire. If I calculate the magnetic field for my first wire here, so that's 2 times 10 to the negative 7, and I1 would be the 1.8 amps. My radius 1 would be the 5 centimeters, so 0.05. I can calculate the magnetic field at this location from that wire. And that would give me 7.2 times 10 to the negative 6 teslas, and it's a dot at that location. All right, so I know the magnetic field for my bottom wire is 7.2 to the negative 7 teslas, and it's a dot. Well, if the net magnetic field at that location is 0, that tells me that the magnetic field from the wire on top of my second wire has to be 7.2 times 10 to the negative 6 teslas, and it has to be an X. It has to be going the opposite direction in order to cancel it out. So for my top wire, I have to have X's at the bottom, which means there would be dots on the top, so the 2 fields can actually cancel out. So now I know which way it's going. I know it's an X for the top wire, so the 2 can cancel out. I can then calculate the current, because this has to be equal to 2 times 10 to the negative 7 times my second current divided by my second radius. And of course, my second radius is the 3 centimeters from the top wire. So doing this, I've got my magnetic field, I've got my 2 to the negative 7, I've got my R. I can find out what my second current is going to be. And this gives me 1.08 amps. Okay, so that makes sense though, because since that top wire is closer, it wouldn't need to have as much current in order to produce the same amount of magnetic field. Now, if we go back to the direction of the current, let's see, I've got dots on the top, I've got X's on the bottom. So again, using my right-hand rule, the second current is also going this direction. So 1.08 amps are going towards the right. So this current is going towards the right, same as the other one, and then the two fields can cancel out. Okay, well, let's try, there's a couple straight wire questions. Let's try a loop question. Okay, so I'm just going to start with just a basic loop like this, and take something really simple. So let's say we have 0.72 amps coming in this way, and then it's going to go around the loop like this, and then just go out the other side. And let's say our loop is 6.5 centimeters wide. And we're just going to find the B at the center. So what's the magnetic field right in the middle of that loop? Okay, well, so first of all, I can calculate it. I can find the direction of it. But if I calculate the magnetic field for a loop, that is mu naught I over 2R. So the mu naught is that 4 pi times 10 to the negative 7. I've got the current. I've got the 2 times the radius, but of course that's just the diameter, which is the 6.5 centimeters. And I can calculate how strong the magnetic field would be inside of that loop. Let's see, that gives me about 1.4 times 10 to the negative 5 Tesla. So that's the field. Now, in terms of the direction of the field, again, sometimes when you got round things, it's kind of nice to switch the function of your fingers to the right-hand rule. So if I curve my fingers around the loop, the same way that the current's wrapping around, my thumb is pointing towards me. So that means there are dots in the middle of this loop. So there would be a dot there for that one right there. Okay. All right. Let's try another question here. Let's bring in some multiple loops like this. Okay. So something like a multiple loop situation. And let's do something really similar. Okay, so let's say we have 140 loops of wire, and we are going to, let's say we got a magnetic field right there. Let's say the magnetic field is, let's go with 7.8 times 10 to the negative 3 Teslas right in the middle. Okay, and let's say that this thing, the whole loop, let's say we got a radius. Let's say the radius is, let's go with 5.8 centimeters. All right, and what we're going to do is we're going to try and find out what is the current. Okay, now first things first, I'm just going to find the direction of the current using my right-hand rule. So in this case, I'd have my thumb pointing down, the thumb pointing in the direction of the magnetic field, and then my other fingers are sort of curling sort of clockwise, which tells me the current must be going around in this direction. So I know that's the direction of the current. Okay, so now I can actually find the actual current. So if I'm going to do that, the magnetic field for a loop, and this time I'm going to incorporate the N for the 140 loops, and I got mu naught I over 2 times R. The only thing I don't have is the current. So the current would be equal to the magnetic field times 2R divided by N, and then the mu naught. So I've got the magnetic field for loop. I've got that value right there. Got the 2. I've got the R. The N, I know, that's my 140. The mu naught is my constant. And then I can calculate the current through the loops. And then when we punch all that out, we get 5.1... we'll say 5 amps. So it's just over 5 amps of current going through it. Okay. All right, well, let's try something else. Let's, here's another set of loops right there. Let's try something like this. Okay. And let's say we've got a magnetic field going through here. And let's say the magnetic field is coming through something like that. Okay. And let's say we've got a magnetic field. Oh, let's go with 0.86 Tesla field right in the middle of the coils. And we'll say that we have, let's go with 480 loops of wire. And let's say we are using inside of the coil, let's say we're using, let's put it over here, let's put it over here. Let's say we're using 0.175 amps of current. Okay, and I want to know how wide is the coil. Okay, so really looking for the radius, but we're looking for how wide the coil could be. Okay, well, we got everything we need. We'll just piece things together. So magnetic field from a loops of wire is N mu naught I over 2R. Really what I'm looking for here is that 2R part right there, because that would be how wide the loop is. So the diameter would just be N mu naught I divided by BL. So we're going to be basically looking for that. So 2R, the diameter, would be the N mu naught I over the magnetic field of the loop. So I've got the N value, I've got the 480, I've got the mu naught, I've got the I, I've got the magnetic field loop, I've got all of it. So I can punch it out and find out the width of the actual loop itself. Alright, so that gives me a very, very small loop, 1.2 times 10 to the negative 4 meters. So that's a really, really, really small loop. But hey, that's just what we got. Okay, and if I wanted to, I could also find the direction of the current. Again, for this one, I want to flip the function of my fingers. I'll make my thumb the magnetic field. My thumb would be pointing towards the right, and the magnetic field or the current would be looping up the back of this thing, coming around, and then coming down the front this way. That would be the direction of the current. Okay, so there's some practice calculating magnetic fields from wires and loops, and you know, the two formulas are kind of similar to each other. They're very similar to each other, but they're not necessarily that hard to use. And we just incorporate some of your right-hand rule that you guys worked on in grade 11.